Okay, this will be the lecture for Chapter 31, and we're going to talk about the quantization of light. Up until now, I've pretty much said I'm not telling you anything that you don't already know, but now things are going to start to get weird, and we're going to start talking about quantum mechanics. We're going to talk about how things at this level, at the electron level, are discrete, and I'll come back to Planck's constant that I introduced last time with this equation E is equal to h times f, where we had energy and frequency. I'll talk a little bit about the photoelectric effect, which is kind of how solar panels work, and what this is going to prove is that light waves are definitely particles. You may be saying to yourself, wait a minute, you said that the double slit experiment proved that light is definitely a wave, and what I'm going to say now is light is definitely a particle. Or we can say that light is either a wave or a particle, or it's kind of both. So we'll talk a little bit about the double slit experiment again. Then we're going to argue that if light could be a particle or if light could be a wave, then particles can act as waves too. And it turns out that electrons can exhibit both wave and particle nature, and electrons are definitely a particle, as we know them right now. We'll talk about how life is basically uncertain, and we'll actually finish off by saying wave-particle duality is actually kind of complementary. So here enters quantum mechanics. Let's talk about quantum theory. It's not very old. We're talking about stuff that is about 200 years old or so. And in the language of science, that's like a baby. Now, a long time ago, again, not very long ago, some people believed that light behaved like a wave. And Young proved that with his double slit experiment, because light is going to interfere, and particles can't do that. Other people, like Isaac Newton, believed that light behaved like a particle. And this fellow by the name of Max Planck came along in 1900, and yes, he is the fellow that came up with Planck's constant. He said light is going to behave like a particle, and it's going to exist in these discrete little bundles, and these discrete little bundles are going to be called a quantum, hence quantum mechanics. Now, the question is, well, who is right? Well, they're both actually right. Now, before we talk about why both of them are right, let me talk a little bit about quantum physics and this idea of quantization. Quantization says that things are going to be discrete. Things can live in certain levels, and they can't live outside of those. And when we talk about the atom, we're talking about quantum physics, and what we're kind of saying is the energy levels, the orbits of electrons are discrete, they're quantized. And the energy in them must also be quantized. Not all values of energy are possible inside of an atom. So if I had a hydrogen atom and I had an electron living in this orbit right here, it's going to have some energy. It may be living in this orbit out here, and it's going to have a different amount of energy. But the electron cannot live right here. It has to live in one of these discrete quantized orbits. It turns out that light is going to be quantized as well, and when we talk about little teeny tiny chunks of light, we're actually going to be talking about these things that Isaac Newton called corpuscles, and we're going to call these things photons. And I've kind of mentioned them on and off throughout here. A photon is a discrete amount of light. It's kind of like a chunk of light, if you will. When I go ahead and I draw these, you're normally going to draw them kind of like this, where I'd say this little chunk right here is a photon. How much energy does a photon have? Well, I introduced this equation last chapter. It's a very important equation. It says how much energy a chunk of light, a photon of light, has is going to depend on Planck's constant as well as whatever frequency of light that we have, where Planck's constant is this value right here, 6.626 times 10 to the negative 34th. Let's just get a little bit of practice using this guy. How much energy does a photon with this frequency right here have? Pretty straightforward. We're going to say E is equal to Planck's constant multiplied by frequency. We go ahead and say Planck's constant is 6.6 times 10 to the negative 34th. You go ahead and you multiply that by the frequency, 0.151 hertz. You go ahead and you type all this stuff into your calculator, and what you're going to get is you're going to say the energy is equal to 9.966 times 10 to the negative 35th joules. Now, this is a really small amount of energy. However, we're only talking about one photon. And when we think about what hits us from the sun, we're talking about millions and billions and trillions of photons at one particular time. They don't have a lot of energy, but there's lots and lots and lots of them. Now, let's just get some jargon out of the way for a second. We've introduced this idea of quantization, and what that's saying is the real world, the natural world, is discrete, or you could even think of it as granular, rather than smooth and continuous like a wave. We've also introduced this thing called a quantum, which is just going to be something that is elemental. It's going to carry energy, and it's going to be quantized. So it's going to have a discrete amount of energy, a certain amount of energy. It is definitely granular. It is not smooth. Okay, now I want to take this a step further and talk about something called the photoelectric effect. And what this essentially is it's going to be if we were to have something like a metal, and we were to go ahead and shine some light on it, it turns out that we can liberate electrons from this metal. We can get a current, kind of the way that solar panels work. But let's talk about this with a little bit more depth. This really bright fellow that you may have heard of by the name of Albert Einstein believed that light actually acts like particles, with teeny tiny discrete quantized chunks of energy, which again are called photons. And they're going to interact with matter one at a time. So right over here, I'm actually going to have my photon. And the photoelectric effect actually supports the particle nature of light. The reason for that is because if I had some light incident upon my metal, then I should be able to increase the amplitude, not the frequency, of my light that's coming in, and I should be able to liberate electrons regardless of frequency. However, that's not actually what happens. It turns out that the energy is going to depend on the frequency, and it's going to be this quantized thing. Adding more amplitude, if the frequency isn't enough, is actually not going to be able to dislodge electrons. Now, this thing called the photoelectric effect is actually going to be how light is going to interact with matter, and it's also going to be related to how matter is going to radiate energy. And again, we're talking about stuff that's only, 100 or so years old now. It was thought of by this fellow by the name of Max Planck, a German physicist. And what he said is any warm body is going to emit energy, and it's going to be quantized. Exact amount of quantization is going to depend on the frequency and Planck's constant, which I've kind of talked about ad nauseum already. Now, let's go ahead and just take a quick look at this. Suppose I had some light, and this light is kind of coming in. Then if it hits some metal that is sensitive to light, then we're going to liberate electrons. We're going to free electrons. Now, very often what we do is we hook this thing up to a battery, so positive and negative, and that's going to set up an electric field. The electric field would go in this direction. We have an electron in the electric field, and so it's going to be accelerated, and it's going to be accelerated towards the positive plate here. Now, what we can actually do is we can actually calculate the energy of the electrons that are ejected from the metal by kind of messing around with this battery. And we could even try to turn those guys around and talk about something called the stopping potential. Now, I want to go ahead and take a look at a simulation for what's going on and talk about the wave and particle nature of light. So here I have a simulation here, and what I can do is I can start to mess around with the light. So here I'm kind of turning the light on, and I'm shining some light on here, and we're seeing some electrons that are being ejected. These are these little blue balls. What I can do to measure the energy of these guys is I can actually turn this battery around and try to stop these guys, and that's going to tell me exactly how much energy these electrons have by messing around with this potential and therefore the electric field. I'm going to set it back to 0, and what I want to now show you is the impact of frequency. If I go to lower frequencies, so if I go to the infrared, then I stopped ejecting electrons. I can even turn the intensity all the way up. I can crank this puppy all the way to 100%, and if light really was a wave, I should be able to liberate electrons. But I'm not. So what this says is energy really is quantized, and energy is going to depend on frequency. It's not until I get my frequency high enough or my wavelength low enough that I'm going to finally be able to eject electrons from this particular metal. And to be honest with you, different metals are going to have different points where they're liberated. This one was sodium, this one is zinc. This one is going to take more energy, and that has to do with the nature of the metal that I'm trying to eject electrons from. This one right here, it's not until I'm far into the ultraviolet that I'm going to start to be able to liberate electrons. Really, it's, how well does sodium like its electrons versus zinc versus copper, and so on and so forth. Now, one really important takeaway from the photoelectric effect is that the energy that this light has is going to be equal to Planck's constant multiplied by frequency. It is discrete, it is quantized. If I were to shine some light onto a metal and eject some electrons, great. If I put more light on, if I increase the amplitude, as long as I don't change the frequency, then what's going to happen is I'm going to eject more electrons, but I'm not going to give them any more energy, because the energy is going to be equal to Planck's constant multiplied by the frequency. The electrons that are ejected have some kinetic energy that depends on how much energy I pumped into the system. Increasing the amplitude, increasing the amount of light, is not going to increase the energy that these electrons have. What this boils down to is that light is behaving like a particle. So the photoelectric effect says light is definitely a particle. Light is definitely not a wave. Just a quick little check your neighbor. Suppose I were shining some light onto some photoelectric surface. The brighter I make the light, the larger number of electrons. It is not the velocity of the ejected electrons. The velocity of the ejected electrons is going to be related to their kinetic energy, and their kinetic energy is going to depend on the energy with which they are liberated from, which is going to depend on the frequency. It's not going to depend on how bright the light is. Now, this slide here shows you something that I showed you with the simulation, but I think it's more easy to digest if you see it in the simulation. Energy is going to depend on frequency, and if I were to shine some low frequency light onto a metal, it might not be able to eject some electrons. So you see this is going up and down relatively slowly. If I were to increase the frequency, I'm going to increase the energy, and then I might be able to eject electrons. So you see up, down, a whole lot faster. Electrons are emitted here, they're not emitted here. Energy depends on the frequency. So light is definitely a particle. Light is definitely not a wave.